Okay, hello, good afternoon, everyone. Thank you very much to have my second lecture on the pipe services this afternoon. And this afternoon, I have prepared quite a number of slides for you, and hopefully I can, accomplish this mission. Okay, this is a possible mission, not impossible. All right, I have checked against the teaching schedule, and first of all, I would like to have a better arrangement about the tutorial. Therefore, I think I think it's better for us to have the tutorial after the lecture finished. Therefore, I would like to reschedule one tutorial session for this series of lecture of the drainage. And let me see. And I would like to suggest, okay, I suggested that, how to get it enlarged? Yes. Okay, here is our original teaching schedule, and we have, the subject examiners scheduled the next tutorial on the 4th of October. Okay, and however, we haven't finished the drainage system, and probably to have a good use of the tutorial sessions, I'd like to schedule it 2 weeks later. 2 weeks later, we have finished the drainage system, and then we can have the tutorial same time. But unfortunately, I cannot reserve the original room. Only the one rooms available to me. Today I checked this morning, is a Z507, one of our original tutorial rooms. So we could make use the same time slot. Okay, same grouping arrangement, but just one minor amendment about the venue for the tutorial. Okay, so I would like to have this arrangement. We schedule the tutorial. Hopefully, this will be better for us for our learning process. Okay. After this lecture, I will send you an announcement via the blackboard. Okay. So we don't have the tutorial session next week, but we postponed to the 18th October, Monday morning again, same time slot. Okay. All right. So this is the first thing. The second one is this. Okay, and for this lecture, for this series of lecture, we're talking about the drainage system, and I put all the information together into one batch, okay, so that you can find all this information from a single location, a single source. And in here, we have, seems to me that here are a lot of files, but only a few numbers I would like to show you during the lecture. One is the PowerPoint slide. And this PowerPoint slide serves for 3 lectures, okay? And therefore I cut this, I subdivide this slide into 3 sections. First section for the first lecture, second one for the second lecture, and so on. And I have also prepared a few number of questions for tutorial discussion, which to be discussed on the 18th. Okay, we schedule tutorial sessions. And apart from that, the rest basically are some reference material. One of them is a list of information, and this list of information I share with Professor Mui, who all the essential table and formulas are shown in there, and which indicated that at least, okay, for examination, for test, at least you will have information available as shown in the list of information. Okay, there's a minimum information provided to you. And also we have some supplementary information for reference only. Okay, and in there I have also uploaded quite a number of references for the British standard, for the CIPSE guide, for some EPD guidelines, for the drainage system and some information and table and flows and drainage menu. All these are just a reference, downloadable from the internet. Okay. However, maybe some of you found quite tedious to figure out all these sources. Therefore, I try to gather all this information for you. Therefore, we will not go through 9 by 9 for those of this sort of information. But to let you know, available to you or to us, we've got a lot of information. Okay. Therefore, as I mentioned that for us, okay, as an undergraduate student, we are able to, after finish the program, okay, we are able to use any kind of design guidelines. Okay, we've got the fundamentals. We are able to apply that. Okay, so here is the information I prepared for this series of lecture of the drainage system for you. Okay. Also observe that those of a copyright material have a restricted use. Okay. Okay, and here is the all right. Here is the PowerPoint I prepared for today, and a drainage system for building. Well, let's go through one by one. Now, we know what's a drainage system. Drainage is basically for a building. We have the appliances. We need to use water. Okay, and what we know, all the water comes from somewhere else, and then after the application, we will drain out all this water. Okay, the drainage system basically to help us to handle those of the effluents generated from our apartments or livable area. And what we understand for a drainage system for apartments, we have the pipes, we have the collecting points. Okay, after all the effluents drain out, go through some process to somewhere else. The entire thing is a drainage from your apartment, okay, up to the disposal. Quite a huge area. Okay, for the building itself, okay, we try to trim the system down to a portion by portion. Okay, now in the lecture, I think we will concentrate into two parts. One is in the building, above ground drainage system arranged for the building to collect effluents from the building. Okay, the second part is within the building site, we need to deliver those of the effluents to the collecting point. This is underground drainage inside the building site. Okay, basically we have these two parts and subdivision. Okay, for the drainage system, drainage is a basic provisions. Basic provision means all the occupiable buildings up to the standard, we need to provide a drainage system. Otherwise, okay, no buildings can be occupied, not permitted at all. So here is a the basic needs. The basic performance requirements is simple, few words. So it's effectiveness, efficiency. Okay, we can further subdivide these requirements into some description, such as the demands. We have addressed it using our demand model to determine what's the sufficient provisions in order to address the water demand. Okay, here's the second point. And apart from that, we have some basic needs on the basic requirements for the system, such as the system should be safe. Okay, we will not cause any harmful effects, okay, to the occupants, okay, to the building as well. Hygiene requirements, okay, and some functional needs. Functional needs is some sort of trade-off. Say, what's the functional needs? Say, water pressure, large enough, insufficient pressure, amount of water, how long for the water supply period, for example. What's the color of the water? Okay, noise generated. Okay, all these are functional requirements. These sort of functional requirements are more or less on the preference a little bit more than the baseline. Baseline means the regulation. We always talking about the regulations. I understand that, but the regulations, people remember, is the baseline requirements. For the building services engineering, apart from on the baseline requirement, okay, we would have the preference. The preference, we're talking about the service quality. All right. So apart from the regulation, we fulfill everything. Sometimes, and most of the time, we will design the system, arrange the system to fulfill some sort of expectation. The so-called the provisional or functional needs. Okay. We will quantify all these terms later. Okay. This slide is a lot of words, but important. Okay. And we try to illustrate what is a good sanitary pipework or drainage system. And just list down some qualitative attributes. So therefore, the principles will apply throughout the entire system arrangement. First, we are going to prevent the transmission of foul air or transmission of bacteria, disease, okay, into the building. We need to maintain that for hygiene requirement, safety requirement. The second, we are going to minimize the frequency of blockage and provide it with adequate pipe access to enable the effective clearance of such a blockage, which is a maintenance requirement, sustainable system. Right? To provide the efficiency conveyance of discharge from sanitary, kitchen, and all these spaces, facility to enable correct function of its appliances. Okay, to maintain the correct operation, effective and efficient requirement. All right, and where any issue is likely to surcharge and minimize the risk of flooding. Okay, also maintain the good use. Okay, normal operation. Okay, and above ground and below ground level, of course. And the general rules shown here, the attribute is the sanitary discharge. Pipework should therefore be kept as short as possible with fill bands, and adequate gradients. Biggest simple is just say simple is beautiful. At least for the drainage system is like that. Okay, do not make your system too compact if your simple system serves the purpose. Be remember in all time. That's important. Okay. Now, for the ease of the discussion, I would like to subdivide the system into the section, just for convenience purposes. Not necessarily be subdivided like that, okay? But for convenience purpose, I would like to discuss the system into using the ground level and the boundary, and above ground part and the below ground part. Why I try to subdivide like that? Because the flow phenomenon, the discharge behavior, and those of the fluid dynamics and fluid mechanics will be very different. For the above ground, mainly the transportation direction is vertical. Okay, below ground mainly for the slope pipe. It doesn't mean that above ground no slope pipe. Doesn't mean that, but the above ground mainly the transmission are the vertical, just for convenience. Okay, so the coverage and scope of this series of lecture, including 3 parts, 2 lectures and 1 design Q&A, also to show you some design information. Okay, and a review. Okay, part 1 above ground drainage today, and next week below ground drainage, and then week after. Okay, therefore part 1. The basic idea in the slide showing here is we try to have a brief classification of system, but the classification of system is not so systematic actually, at least not systematic to me. Okay, when I was a student, I feel very confused about that. But I try to pick out the basic idea for the classification purposes from various textbooks. The first one, we're talking about the separation of effluents. The separation of effluents actually is for the processing, the further processing. Okay, and according to this basic idea, we will the example shown there is we separate the effluents come from the soil appliances and from the waste appliances, which their effluents, the water quality are very different. Okay, one from the water closet, more maybe I say dirty water. Okay, maybe some textbook refer this as dark water or black water. Okay, from water closet you may know bitter or similar. Okay. In contrast, okay, to the soil appliances, we will have the waste appliances. Relatively, those are the water less dirty, okay, and some textbook may refer those effluents are gray water in terms of color, okay, such as wash basin, bath, fountain, shower, okay, something like that. And classification of these two, because of the processing, the handling will be different. May be handled by different discharging pipe in the building, okay, and then they join together somewhere else, or go to final destination for different process for water treatment. Okay, it's depending on the final process. But anyway, if we are going to separate the effluents like that, the idea is over there. Other sources apart from the appliances, we probably come from the rainwater is one of the sources that we use the water nowadays. We have some recycled water as well inside the building. Okay, so apart from the two different kinds, different class of effluents, maybe we have the more, okay, in the actual building. All right, so according to this idea, the separation of effluents, we can arrange the system into different outlook, a different appearance, okay, such as a so-called a two pipe, one pipe, things like that. Okay, I think we just go for the example, so-called the two pipe and one pipe. However, unfortunately, the definition for two pipe and one pipe are not so rigid. Okay, when you look at the design guidelines, look at the textbook, you will feel confused. Okay, just put an example, the idea, very basic idea. If we are going to separate the effluents come from the soil waste and the wastewater, this is becoming a so-called a two-pipe system. The pipe referring to the drainage stack. Okay, drainage stack actually is a vertical arranged drainage pipe work. Okay, so-called a stack. Okay, and with this, I've got the question, why did they join it together finally? The separation is only applicable in this example, applicable inside the building only. All right, so that the routing for the pipes may go through a different location, having different the requirements, so that the processing including the transportation as well. But anyway, this illustration try to illustrate the idea, the separation of the different effluents into two different stacks, and so-called the two-pipe system. In contrast with that, they can be arranged together, becoming so-called a one-pipe system. Okay, a single pipe collecting both classes of the effluents as well. Okay, that's fine. That's okay. I use the screen. Okay, I use the screen here. Okay. Thank you. This is a one-pipe system as well. Okay, thank you very much for. Okay, so we have a further example there, but mainly if we are going to have only classification due to the separation, is a one pipe, two pipe, maybe more pipe for the different effluent classes. Okay, we skip this view, and we are going to have the second idea. The second idea is about the ventilation. How the ventilation is arranged, come up to the classification. Now, for the pipe here, we have the water discharge at the level. Okay, and then, very interesting. How about this part? No water. Okay, not for the water discharge, but for that part is for the ventilation. Ventilation is to serve the purpose, the purpose of balancing the pressure inside the pipe work. okay, so that the foul gas will not ingress to the occupied area, okay, to balance the pressure, to have a proper isolation using the water seal, okay, in the water trap. Okay, we will detail the water trap operation later on, but basically we try to confine, okay, all the foul air inside the pipework. Okay, get it isolated from occupied space. Therefore, we need the ventilation. How this ventilation be arranged and come up and contributed to the system classification. Okay, for the pipe here, we extend the drainage pipe work to the outdoor air, and this part so-called the primary ventilation pipe. Okay, usually textbook most likely call it as a primary ventilation. Apart from that, in contrast, we see, okay, I used here, sorry. Here's an additional pipe work. This pipe work not for water, okay? No water can flow into there. And this also serves for the ventilation pipe. This additional ventilation pipe, so-called a secondary ventilation pipe, okay? If the pipe arranged vertically, usually we'll refer, they are stack, ventilation stack, something like that. Okay, so we have the basic idea and the component mixed together in order to have the classification of the system. Please do not use a terminology, say, my design is a one pipe system. Actually, one pipe system, you need to describe further to better describe it, better define it, how one pipe is your system will be. Okay, because a lot of variations. Okay, we skip this. Okay, go to a design guide. I have upload the entire design guide I found from the internet. Okay, don't charge me, no copyright. Okay, now not the copyright. Okay. Now, the definition I quote from the Institute of Plumbing, which is a chartered institution. So I think there will be of some status, okay? Now, the primary ventilator system, talking about the ventilation is supplied by the drainage stack itself as arranged in the figure there. All the ventilation from the drainage stack, ventilation is from there. It's a primary ventilator. All right. So the description is there. Apart from that, we also have the basic piping for secondary ventilation. Apart from the primary ventilation, we are going to have one more ventilation stack acting only as the common connection to ventilation pipe, could be like that, and to vent some of the location inside the pipework. Okay. In the case, because the ventilation is sufficient, we need a secondary ventilation as well. Okay, and if for those arranged differently from the previous one, they will call it word so-called a modified one. Modified also a confused word, not well defined. Deviate from the previous one is so-called a modified, and how modified it, we need to further describe it. Okay. Now, second ventilation system. This is a secondary ventilation pipe, and the ventilation location to the various locations where needed, particularly for the WC, as they require much more air. Okay, here's some definition. Okay, the ventilation location could be at the appliances, could be at the drainage stack, could be at the branch pipe as well. So now we've got a different alternative. However, for the alternative, somewhere have to vent, somewhere not to vent, which we need to go through the experimental study to see whether the seal loss will be there. Okay, for the pipe with a limited length, more than that, we need ventilation, something like that. Mainly for those of the dimensional requirements come from the experimental data, mainly. Can we calculate it analytically? Theoretically, is almost impossible. Okay, and some solutions are not available in the analytical form, only available in a numerical solution. Therefore, for us, okay, as an engineer, we will not spend whole year to solve for the one pipe size, okay, but relies on the experimental data, okay, to design entire building within 1 week, things like that. Okay, performance requirements we did mention simple, safe, so we not go through the word by word. And apart from that, we also have some technical aspects. I try to give some more description on those so-called technical aspects, such as the flow requirements. We've talked about that. The smell and foul air, which require the ventilation. I did receive some calls from the local developers talking about the bad smell. And this is related to the ventilation, okay? And the solution, some sort of existing apartments, okay, with the window, okay? And basically, there should be a ventilation problem. To limit the noise, okay, flushing WC create noise, okay? Too noisy close to the back room will be a problem, right? Be durable material, be maintenance. We can conduct the maintenance easily to replace the system easily. Okay, the system be traceable. We can trace the pipe work, where the pipe works, and once the leakage, how to repair. All these are important. Subject to some the so-called technical aspects. Okay, and also common to a lot of different surfaces. Okay, efficiently, okay, to carry away the soil and waste product efficiently, immediately, quietly, effectively. Okay, you put in all this work. This is the basic consideration. Must not lack, and okay, all right, we skip all this. Be testable. Okay, we need to provide some space for testing the pipe work, for the leakage, things like that. Okay, we skip all this because quite detailed. You cannot read the wording. Okay, now we go to the details about the piping arrangement. For the piping arrangement, we subject to various philosophy. Okay, and apart from those basic assumption and parameter adopted there, okay, common to all those requirements, we will have different appearance of the piping layout. Therefore, I would like to stick to a few numbers of a layout example to serve the purpose of discussion. Here is the example of the piping arrangement in Hong Kong, and we will refer to the documentation detailing the piping, such as here are the source, the buildings regulation. Okay, in the building regulations, the chapter 123 is the buildings regulation. The subsidiary I, 123I, not 1231, which is for the drainage system. Okay, apart from that, because the Hong Kong Arctic City, the legislation system is the performance-based. Performance-based means it will list down the requirements qualitatively, not necessarily quantified, so that which allow an engineer to, based on the engineering principles, okay, to provide a solution to address the performance requirements. Okay, this is the local legislative systems like that. Therefore, based on the cases and your the basis information, say design guideline, the standard, you can have the variations of system, a different smart system in order to address the requirements. Once those designs acceptable, this will be a showcase, things like that. Therefore, the second bullet point showing the example sizing may refer to the plumbing service drainage design guide, or the corresponding to British standard, or corresponding to some other standard which be acceptable to address the performance requirements. Okay. Why the British standard? Why the Institute of Plumbing? I think here in this city we have the historical reasons. A lot of buildings already designed to those of the requirements. Okay, and in those of the design guides, we do have the table values. We have the figures and charts in there. Apart from the England one, some okay, I show you later on. All right. Now in here, I'd like to show you an information comes from the British Standard first. A British Standard is interesting now. This is so-called a BSEN. Maybe later because the Britain gets separate from the mainland Europe. Okay, therefore no more EN later on. I don't know, but the point is that documentation available here, so-called the BSEN, they have an objective or aim to provide unification of a standard, okay, across the big borders in the European countries. Okay, therefore so-called a BSEN. Therefore, inside the BSEN, they define the different kinds of system to put it documented so that the documentation could be applicable across the different countries, different nations, different areas. Okay, maybe I jump to the last one first. Okay, now in the BSEN, okay, I should here. They try to classify the system into 1, 2, 3, 4. 1, 2, 3, 4 is not the classification of BSEN, but the system 1, 2, 3, 4 is a description to the basic underlying assumption adopted by different nations. Say, for the German, Austria, Switzerland, Belgium, they will adopt a set of underlying assumptions in order to lay out the pipework. For the Scandinavia, they have another idea to lay out the pipework. Okay, for the UK is a system 3, for the France a system 4. Maybe for some other countries system 5 and 6. Okay, but basically it's classified into 4, described into 4, in which the differences of the basis is like that. Is based on the feeling degree. Feeling degree is the idea. The idea is how a branch pipework to be utilized. Okay, the feeling degree actually refer once we have the effluent discharge through the branch pipe, something like that. Okay, actually, indeed, all the water flowing through the pipe will not, most likely, will not occupy the pipe entirely. We will allow some space for the air flow, and this air serves for the ventilation. Okay, it could be like that, partial filtered flow, not necessarily fully filtered. Okay, and the area filtered up by the wastewater becoming described by a word so-called feeling degree. Okay, if the pipework, the branch pipe allowed to fill up by 50%, this is becoming system 1. 70% becoming system 2. Okay, 100% becoming system 3. Other than system 1 to 3 will be system 4. Therefore, system 4 are not well defined. Okay, now on this classification, the basic idea is we can appreciate that even the same pipe, same appliances. Okay, at different countries you will find, okay, this appliances, why the pipe is smaller. Another area, okay, it's the same arrangement, the pipe seems larger and longer. Okay, therefore, actually, the arrangement is that based on the experimental study, the data arrangement, all this set of design can fulfill the above mentioned requirements. Okay, so based on 1, 2, 3, 4, actually we do have the different sets of the piping layout outlook there, right? The differences is over there. Okay, so in here we need to confine our discussion, otherwise are too confused. Okay, okay, we try to confine later on the British system, and I think maybe you'll be easier to follow one of the design guide. I think this will be easier for you. All right, but before that, I would like to illustrate the entire bigger picture for you. Okay. Now the primary ventilator system configuration, as we mentioned, that primary ventilation is come from the drainage stack mainly, and the ventilation is mainly come from the extended part of the drainage stack up to the roof level, above the roof level, okay? And the regulation nowadays talking about the exhaust point of that pipe opening have to above all the occupied area, at least certain distance above the roof, 1 meter, okay, for example. But maybe recently we found 1 meter may have some problem. Or anyway, now in the British standard, apart from the primary air from the drainage extended part, also come from some components. These components are not necessarily approved by all the cities, not universal. This is so-called a air admittance valve. Okay, just like non-return valve, one way air can come in, no air can go out. All right, and puts a physical isolation. This is allowed for some European area, okay, not for Hong Kong until this moment. Okay, apart from that, also if you've got two pipe, therefore extended the stack up to the roof level, called the primary ventilation. So that this arrangement, so-called the primary ventilator system. Okay, apart from that, we have a secondary ventilation. Additional vent pipes is provided. Okay, additional vent pipe is provided. Here joined together because both are vent pipe. Okay, unvented system, unvented parts are not the system. Unvented part we found here is the branch pipe without any ventilation. Okay, it's possible, but have limited length. Longer than that, we have to supply the ventilation. Okay. And for the branch pipe with the ventilation. Okay, with the ventilation. It's depending on the length, the gradient, and pipe size. Okay, having the ventilation, the pipe can be longer. Okay, the less restriction about the pipe routing. No ventilation, we have a more strict requirements about the pipe gradient, pipe diameter, pipe length, things like that. Okay, so the classification in here, which help us to use the correct set of information to lay out the pipe work. Okay, and then here we have some list for us, okay, to detailing the terminology and for the standard. Okay, we skip this. Chap 0 highlighted. I will give you some more details about that later. Okay, air admittance valve. We have discussed this component. This component is just like non-return valve. Okay, look at the picture there. If the negative pressure created inside the pipework, air can be refilled from the surrounding atmosphere. However, if a positive air pressure inside the pipework, the valve will close. Okay, and therefore no foul air will go out. And this ideally, okay, the location can be installed inside the occupied space. Okay, no need to extend the ventilation pipe up to the roof level. That's the advantages. Okay, now this page is misplaced. Okay, okay, but anyway, for the classification of the system, okay, and the layout principle, the layout details will be listed in the table form. So according to the system arrangement, the system underlying parameter adopted, we do have the different parameters for the system. Here are some example tables, such as the air flow rate for ventilation, such as the drainage, the drainage capacity of the stack. Although for 1, 2, 3, 4 put it together, okay. in there. We have two columns. One column is okay. One column is a square entry, street entry. Actually, you can find the definition for that. Now, basically, square entry is the pipe just a full get connected to the step. A street entry, they have a smoothen water flow. Okay, better smoothly flow the effluents into the drainage step. The differences is that they will create less pressure variation. Okay, so that less pressure variation, the drainage capacity will be larger as compared to the square entry. Okay, we are not talking only about the filling degree at the stack, but also the air pressure generated inside the system. So that we consider both in there, the complications over there. Okay, water seal, we highlighted at the park. Every sanitary appliance should be provided with a trap. Okay, this is a water trap inside of water filling, the trap, so-called the water seal, because the water is used as a sealing material, okay, between the foul air and the occupied space to provide a physical isolation between two areas, isolating the flow air from the occupied space. So it's sometimes I use the term is a water seal, sometimes is the waste traps or things like that. Waste trap is a physical part. Water seal is the water inside, functionally. Okay, on here are some requirements about the waste traps arrangement. The waste trap, basically the waste trap should be close to the appliances. But for some appliances, according to its arrangement, okay, they may a little bit away from the point of utilization, okay, such as the shower. The arrangement may not be so convenient, okay, at the point of drainage. They are allowed to some distance. Apart from the water seal part, the figures are not shown here. I put you an additional information. Here is 14. Separately, which is for the point number 4, so-called the proprietary valve. Okay, it's something like this. Okay, I uploaded the pages to you additionally this morning, which is an example for the so-called waterless trap seal. Waterless trap seal, the isolation is not come from the water, but come from some not the membrane, some plastic bag. Okay, the arrangement, the trap is something like that. Water can go through it. After the water goes out, okay, the plastic will adhere together. Okay, so that after adhere, the gas, okay, flow gas cannot go out. Okay, and this is some sort of plastic. Okay, have an elasticity, things like that. Okay, the product not yet allowed for Hong Kong. Is I don't know for future, maybe probably possible. Okay, the page here. Now, the purpose of this waste trap is to provide non-mechanical barrier, okay, to prevent the escape of flow air into the building, okay. But in addition, the water reservoir can act as a dilution feature to intercept small accidental drop of objects. Okay, their descriptions like that. Let water go, okay, but no flow air in. That's the idea. We do have the different design of the trap. Okay, just observe some using the pipe having a bend, some make it into the bottle shape. Okay, the bottle shape can be detached so that we can remove all the deposition, the sedimentation inside. Okay, so that we come up with the different applications. Say for bottle, usually apply in the wash basin and kitchen sink, which used to collect those of the small objects inside there in order to remove the blockage and things like that. Okay, and there should not be more than one trap. That's the principle still applicable Hong Kong. We have only one trap between the appliances and the drainage step. Why not two? Because more trap means more risk of the blockage. Once blockage, the wastewater comes out, will cause the hygiene problem more than, okay, the additional trap. Okay, so this here is balance. However, there's quite a long discussion from 2003 after SARS about the second trap. Some building, some application, they try to have the for the demonstration purpose to have the second trap. Okay, but still not yet come to a standard design. Okay, but the basic idea is only one trap in order to maintain a efficient discharge. Very beginning, we talk about the principle, efficient discharge. The minimum depth of water seal is required. Okay, I put in the latest slide. Resealing trap, anti-vacuum traps. Okay, it's an additional design in order to maintain the water seal inside the trap. Okay, will not be draining out. Okay, the minimum requirements is 37.5. This is a magic figure. Okay, the magic figure here, whatever the trap seal design, after the operation, the water will follow the wastewater to flow, right? And then resealing, after resealing, we have to maintain the minimum height of water inside the seal. And this height of water, here, actually will create the pressure of the water column. So that one side air pressure variations have to go through this column of water before the air can passing through it. So that this height will create a sufficient pressure, and the pressure corresponding to this water column becoming the rho density of water multiplied by gravity multiplied by the depth, rho GH. Okay, therefore approximately for the 37.5 mm is approximately 375 Pascal, plus or minus. And some for engineering, for accuracy, we will mention, say, around 38. Okay, why some we do have some appliances have deeper water seal? Because for some others, say for the WC, there's a flushing. Okay, the flushing having quite a large momentum. And this momentum will cause the seal loss. Seal loss means some of water following the flow and discharge to the step. Insufficient water to refill, to backfill the trap, so that the water seal drop. Therefore, the standard, okay, for the seal depth, okay, inside the trap have to be designed to the deeper one in order to compensate those of the situation having the water lost. Okay. All right. We're talking about the loss of water seal. There's a lot of causes. The main causes we have to avoid is a siphonage action. Siphonage is describing the water will withdraw or water loss is due to the excessive pressure variation. Okay, and this excessive pressure variations can be induced, can be created by the discharge action of the appliances itself. Okay, if the classification here is just a description, the description is that self-siphonage and induced siphonage, also talking about a siphonage action. But the siphonage source, if the siphonage is due to the appliances itself, okay, is a so-called self-siphonage. If the siphonage action is due to the discharge of other appliances, okay, the water seal trap, no water discharging, but the discharge comes from the appliance A, but the siphonage action created at the location of at B and C, the so-called induced siphonage. Whatever the induced siphonage or self-siphonage, okay, the principle are remaining unchanged, the same. Okay. Now for the discharge action here, of some arranging pipe length and the gradient, okay, now the water start to flow in there, okay. Because of the gravity, the water will accelerate, okay, and keep on accelerate until the friction created by the pipe be counter-reacted at the same magnitude with the acceleration due to gravity. Down the water flow becoming at a steady, same speed, a so-called a terminal speed, okay, or terminal velocity, which is a balance, okay. Now, if in the case, because the fluid mechanics, the partially filled pipe, the flow velocity is different from the entire filled pipe, okay. Now, for this illustration, because the water column flow into the stack, accelerate, okay. However, the refilling water from the discharge not yet come to its position. So it's run faster and the incoming water slower. What does it mean? What will happen? They will create so-called a partial vacuum. Just like you draw some air in the column okay, with some force, no supply to air. This will create partial vacuum. This partial vacuum actually will draw the water from anywhere it get connected to. All right. If this partial vacuum is large enough, okay, it's possible to draw the sealed water inside the trap, and because we have no more water incoming, therefore we come up with the seal loss. All right. Similarly, and this partial vacuum is an area will transport through the pipe, will flow through the pipe, okay, such as from one partial vacuum from one location, okay, go to the second location. Once the partial vacuum, okay, go through here, all the traps will be affected. The partial vacuum not necessarily with water, okay, some sort with the water with the air wave, the pressure wave, transport through the entire pipework. All the seal trap get connected to it will be affected. Okay. Apart from the siphonage action, we do have some other possibilities to the water seal loss, such as a back pressure. Back pressure will be okay. We need to ask, where is the pressure originate? Change of the flow rate inside the pipe. For steady state pipe, usually we do not have the pressure transient created. All right, unless we have the change of the flow rate or change of the direction. Okay, for the here is a change of the direction, also change of the flow rate. Same flow rate. Okay, flow velocity. Okay, because the water comes here, drop. The terminal velocity is different from the slope pipe. Okay, also more water come, and here the flow is slower. Here also we so-called a hydraulic drum. Hydraulic drum means there are some fill location, some pipe location got entirely filled up by water. So the water continues jump into that, go into that, will create a positive pressure in some area, particularly at the main drain, building main drain at the band location. Therefore, in the previous some table I show you are at the building base, the band have to be large band or specially arranged in order to mitigate or minimize the effects due to the positive pressure. Okay, here this generation is a positive pressure. If the positive pressure region is there, there are possibility some air will become out. Okay, if you go to the YouTube, just try to key positive pressure. I'm not sure if the YouTube is still there, but you can see some experimental showing the positive pressure, the WC just like a fountain, okay, just a fountain and get the entire toilet wet. Okay, apart from that, we also have the capillary attractions, such as, for example, some of us like to use the facial tissue. It's different from the toilet tissue. toilet tissue get wetted and then will be broken into small pieces because those of the tissue are short fiber. All right. For facial tissue, it's not easy to be detached in small pieces because they are the long fiber. We use those long fiber put in there for flushing. Sometimes there's some residual in here. This residual will attract water. All right, get easier to be blocked. Therefore, I advise don't use the facial tissue for toilet purposes. All right, apart from that, also the wind pressure. If we have subject to the strong wind, okay, you have the ventilation. You did study the ventilation, study the pressurization. Okay, there's a wind effect. Same equation. Wind passing through it will create a negative pressure. The negative pressure, if large enough, would affect all the shield or water shield. Okay. So just some description for that. Wind pressure, the same equation, rho v square. V is the velocity of wind. Rho is the density of air. Okay. Discharging momentum, this also may affect it. I do not go into the very detail about the mathematical calculation. This is unnecessary because for those of the parts, we're talking about is the design of products mainly. For some, okay. Apart from that, okay, we have a several design so-called a resealing trap. Resealing trap is a special design which we cannot entirely avoid for the negative pressure. But the trap will be designed to have several space to reserve the water inside. Additional water will allow the air to go. Okay, this additional water, when they reseal the trap, still can maintain the sufficient height of water seal. This is a special design. Here is just one example. Not only we have a Macapine, the sealing trap, we also have some other designs, such as the next one. Okay, this is the next one. All right. Apart from the resealing trap, also we do have some design. These are now becoming quite a standard design. Is a long return valve. This is an air emittance, small air emittance component attached to a bottle trap, in which here is a small valve. The valve allows the air coming in and no air goes out, just like an air emittance valve. Okay, be manufactured into a set. Okay, this we can skip. All right, maybe I just stop it here for a while to have a break. Okay, I talk quite a lot, and okay, maybe we have a 10-minute break. Okay, we will resume 10 minutes later. 20 to 5, we'll resume the lecture. Okay, just enjoy to have a break to visit the toilets, to buy some drink. I'll see you 10 minutes later.